So the first part of the lecture will be on declarative data mining. So I will overview some related works on this topic and detail some contribution on declarative data mining using CP, constant programming. So what is data mining? Data mining is at the core of the knowledge discovery in databases. This involves different challenges, such as designing efficient tools to tackle data and the discovery of patterns of potential user interest. So the heart of the mining process is the discovery of regularities and interesting phenomena in the data in easy understandable terms. So such regularities are called patterns. For example, if we consider here the example, we have some biological situations described by a set of genes here. A frequent pattern is a set of genes which are frequently found in many biological situations. For example, here we have the pattern constituted by two genes, G1 and G2. As we can see here, this pattern is frequently present in some biological situations. So pattern mining methods are the prime example of data analysis tools. So a pattern here is typically defined as recurring structures in the data. For example, here a pattern constituted of G1 and G2. So the user specifies the type of pattern to be mined, and the miner use techniques to find the required pattern. So many techniques have been introduced for mining traditional patterns, like a frequent item set, association rules, for example. So beside the extraction of item set, one can consider another relation between the data in the form of sequences. So here we would like to mine what we call sequential patterns. So here we consider some relation between data, like the order of appearance of this data. So sequential pattern mining is another topic of data mining concerned with finding a relevant pattern between data represented as sequences. So other forms of data can be considered, like trees, graph, etc. So in this lecture, I will focus mainly on item set mining task, but there exist plenty other tasks of great interest with different applications like clustering, association rules mining, etc. So as I said before, item set mining is one of the most studied problems in data mining. It was originally introduced for sale transaction, or what we call market basket data. Here, a transaction transaction is so the goal here is to find regularities, like the set of products that are frequently bought together, or people buying some product usually buy another product with it. So more formally, let I be a set of items or attributes. An item set X is a non-empty subset of I. So given a set of transactions or object, a transaction database here is defined as a multi-set of item sets, where each transaction here, or I, is an item set. So we define the cover of an item set as the set of transactions where the item set appears. The frequency of an item set is the cardinality of the covers. So in terms of size size of the search space, we have 2 powers the cardinal of the set of items. So we can have an exponential numbers of patterns. So the search space is very huge. So in literature, we can find 2 kinds of representation of the transactional databases, namely the relational representations, where objects or transactions are described with Boolean attributes in I, or transactions are presented as array of subsets. So here, if we consider the relational representation, we have just to say if some items are present in the transactions. But in the transactional representation, for each transaction, we report all the items that appear in this transaction. So in this talk, I will consider indifferently the 2 representations. Here we have some example. For instance, if we consider the following databases, we have 4 transactions and 3 items, and we, for example, here item A1 is present in object or transaction T1. So we put 1 here, and if the item is not present in the transaction, so we put 0. But here, with the transactional representation, which we call the classical representations, we have for each transaction the description in terms of items. So, given a transaction database and a minimum support thresholds, we note here theta, the frequent pattern mining problem is the problem of finding all patterns P such that their frequency are above the minimum support thresholds. So the input is the transaction database and a minimal support thresholds, while the output is the set of all frequent item sets. For example, if we consider the following transactional database with 3 items, E1, E2, and E3, and 4 transactions represented here by object 1, 2, 3, and 4, if we set the minimum frequency threshold to 2, we can get 5 item sets. For instance, if we consider the pattern E1, E2, we can see that this pattern is present in 2 transactions, E1 and E2. So the cover of E1 and E2 is constituted by transaction E1, O1, and O2, and its frequency is the cardinality of its cover, that is equal to 2. So this is a formal definition of frequent item sets. You consider a query. We ask for a pattern. This pattern may satisfy a certain query expressed by set of constraints. For example, here we consider the frequency constraints. That means that the frequency of the pattern must be greater or equal to a minimum support threshold theta. But already early on what was recognized, the output of frequent pattern mining algorithms was too large and too redundant to be useful. So this phenomena is called pattern flooding. For instance, consider the following transaction database. We have 15 items and 8 transactions. So how many frequent patterns are there? So here we can have the following number of patterns, okay? But if we look at the different patterns we can get, actually we have potentially 3 interesting ones, these following 3 patterns. So To address the problem of pattern flooding, many researchers focused on selecting a small subset of patterns, and different approaches have been proposed. The most popular one is what we call the condensed representation of frequent patterns. So I will detail now what means the condensed representations. So here the item set are organized in equivalent classes with respect to their frequency. Here, equivalent classes includes item sets that have the same frequency. For example, here on this following databases, transaction database, we have, with respect to the frequency, we have 3 equivalence classes. The first equivalence classes here correspond to the item set with frequency equal to 2. The second equivalent classes is constituted by item set with frequency equal to 4, and the last equivalent classes is constituted by item set with frequency equal to 5. Okay, so closed item set are those that are not that do not have any super items, any superset with the same frequency. So they represent the maximum item set within equivalent classes. For example, if we take the following 3 equivalent classes, on the first equivalent classes, we have ABC as the first as the closed item set. In the second class of equivalence, we have BC as the second closed item set, where in the third one, we have C as closed item. So on this transaction database, we have the 3 closed item set. So this closed item set can be seen as lossless compression of the set of pattern of the set of frequent item set. It is a lossless compression because from each closed pattern we can find the frequency of all the pattern in the same equivalence classes. So this representation is of great interest as they reduce the output of the pattern mining algorithms. So formally, we define the set of closed pattern of closed item set with the following formula. This formula expresses the fact that an item set is closed if it is frequent, but none of its proper supersets has the same supports. So with this definition, we get the following proposition, if you want. Every frequent item set has a closed superset. So in terms of mining, a brute force approach that explore all possible item sets is usually infeasible due to the size of the search space, which is exponential, as said before. Thus, to be efficient, several mining algorithms exploit some interesting properties on constraints like the frequency constraint here to discard some irrelevant patterns. So we have the following relation between patterns and their cover. So if we have an item set X, and so if we have an item set Y and an item set X, which is a superset of Y, so we have the following relation. The cover of Y is included in the cover of X. So it follows that the frequency of Y is below the frequency of X. So this property is very important as we can deduce some interesting properties that is expressed here. If an item set is extended, its support cannot increase. So one can say that the support is anti-monotone or satisfy what we call the downward closure. So this property is very important as we can infer the following relation. So if, for example, if you have the following relations, okay, the frequency of y is below the frequency of x, such that x is the superset of y. So if the frequency of x is below y, or that means x is infrequent, so y is infrequent too. So here the relation, the property, the nice property that we can infer here is that no superset of an infrequent item set can be frequent. So this property is very important and exploited by all mining algorithms to prune the search space. So of course, the contraposition of this application also holds. So why declarative approach? So there exist plenty of efficient specialized methods for mining frequent patterns or frequent close patterns, but all these approaches suffer from a lack of what we call genericity of flexibility to handle and to push simultaneously sophisticated combination of various types of constraints. In fact, new constraints, if we have to take into account a new constraint, we have to encode this new constraint and their combination often require new implementation. So there is limited flexibility. So the question here is that rather than having to develop a new algorithm for every data type or pattern type, etc., one can also ask whether there does not exist a general meta model that can be parameterized accordingly and used to declaratively and efficiently discover the pattern of interest. That is the main idea here with the notion of declarativity. So the prototypical approach in this school of thought is to define the problem at hand in terms of constant programming and make use of readily available constant solving tools to do the heavy lifting. So that this is the interest of using the constant programming. So we have many advantages. The first advantage is the reusability. We can reuse the solving technology for different problems. We can have some kind of incrementality by adding or removing user constraints. We can also benefit from the exhaustivity and optimality offered by the CP solving approaches. So now I will review some related works about on this topic. So we have several works have been investigated the use of CP or SAT techniques for data mining. See here we have some important works in this field. As you can see here, this concerns different mining tasks like pattern mining, more particularly item set mining or association rule minings, sequential pattern mining, sequential mining, clustering, and more recently, we can find some works on classification. So what is CP? Constant programming, as you know, I think, is a powerful paradigm which offers a generic and modular approach to model and to solve combinatorial problems. So a CP model consists of a set of variables, okay, and set of domains mapping each variable to a finite set of possible values and a set of constraints. A constraint here expresses a relation that specifies the allowed combination of value for the variables that appear in this constraint, what we call the scope of the constraints. So a solution is the assignment of all the variable in X, satisfying all the constraints of the problems. So constraint solver typically use backtracking search to explore the search space of the parcel assignment. So this is what we call the enumeration steps. So the main concept used to speed up the search is what we call the constant propagation or filtering. So filtering is the process of reducing or removing values from variables which do not participate in any solution. Why? The propagation is the mechanism of propagating the consequences of any modification on the constraint which involves the variable whose domain has been modified. So let me show you an example. If you consider the following CSP constituted by two variables, x1 and x2, with the following two domains, if we impose the constraint x1 is greater than variable x2, so the filtering of this constraint will remove values from the domain of x2 that are greater to the maximum value of the domain of x1. So we can remove value 2 as the maximum value of the domain of x1 is 2. So we can remove from the domain of x2 value 2 and 3. Now, if we add a new constraint, an equality constraint between the variable x1 and x3, so we can reduce the domain of this variable to 1. So we can remove value 2 and 3 from the domain of x1 and x3. Now, as the domain of the variable x1 has been changed, so we need to propagate this modification on the initial constraint, on the first constraint, x1 greater than x2. So this propagation will remove value 1 from the domain of x2. So here we have a complete filtering, which means that we cannot remove any other value from the domain of x1, x2, and x3. So another important modeling tools in CP are what we call the global constraint, which allow the expression of a complex relation involving an arbitrary number of variables. So a well-known example is the all different constraint, global constraint, which force variable to take two different values. So the benefits of using global constraints is twofold. First, in terms of expressivity, since they can represent a set of constraints in one global constraint, but also in terms of resolution, better filtering. It provides a more global point of view, which results in stronger filtering. So here filtering are often implemented with the help of other paradigms like using algorithm on graph, for instance, to find the most of a pattern, which is the longest pattern, shortest patterns. We can also exploit the notion coming from network flows, for example. So all these techniques can be exploited to provide efficient filtering that can be associated to some global constraints. Okay, so now I will give you some details about the first proposal that make the connection between pattern mining and constant solving. This model is what we call CP4EL, proposed by Luc Deret and his teams. This model is based on what we call reified constraints to connect two kinds of variables, item variables and transaction variables. So let me detail you these two kinds of variables. So for this model, we define, let X be the unknown pattern we are looking for. So a Boolean variable xi will be associated to every, here we introduce Boolean variable xi for each item. So for each item, we introduce one Boolean variable xi to represent the presence of items in the item set. So xi is equal to 1 if and only if item I is present in the item set X. So the second kind of variable are here X is the decision variable, but we can found a second kind of variable, what we call variable on transactions. Here, for each transactions T, we introduce one Boolean variable, transaction variables, to represent the fact that the item set X is present in transaction T. So if the transaction variable is equal to 1, this means that the item set X is included in the transaction T. So in addition to this variable, we use a binary representation of the dataset to represent the presence of the items I in the transaction. This is given by this matrix DTI. So if item I is present in the transaction T, we have value of 1. Okay, so from this model, after we have defined this variable, so we can impose some constraint. So the most popular one is the coverage constraints. So the coverage constraint is here encodes the cover of an item set. So it ensures that the variable transaction associated to transaction T is set to 0 if and only if the item set X is absent from T. So the second constraint is the frequency ones. So this frequency constraints ensures that the item set X is frequent with respect to the some thresholds value theta. So we have we just need to sum up all the transaction variables to verify if the item set is frequent or not. So one can also add some redundancy constraint, like this one, to perform power pruning. So I will not give much more detail on this model. So I will just show you an example on the modeling of this kind of constraints. So if you consider here this model, this transaction databases constituted by 3 items and 4 transactions. So we have here the CP model based on verified constraints. So we have the 4 coverage constraints. Okay, we have 1 frequency constant. So we have the sum of the transaction variables. So this sum must be greater or equal to 2. So we suppose that here the minimum frequency threshold is equal to 2, and we can add some redundancy constants. So for example here, as you can see, x1 is equal to 1, if and only if. So if x1 is equal to 1, that means that transaction variable, the sum of transaction variable are equal, greater or equal to 2. This is, so if we see at the transaction database here, as item 1 is present in the 2 transactions, so the sum, so this item to be present in the item set, we need to have that the sum of the transaction variable associated to T1 to 2 must be greater or equal to 2, and so on. So from enumeration to propagation point of view, so if we start the enumeration by assigning the first item variable to 0, or x1 to 0, we can deduce that transaction variable T4 and T3 take value 1. If we look back at the CP modeling, so as x1 is equal to 0, so we can infer that T4 is equal to 1, and if x1 here is equal to 0, so we can infer that x2 is equal to 0. So the transaction variable T3 must be equal to 3. So by assigning value 0 to x1, we can infer that the transaction variable T4 and T3 must be take value 1. And so we can assign 0 to the item variable x2. So from this situation, we have a choice between assigning, as we have the third variable x3. This variable may take 2 values, 0 and 1. So if we assign value 0 to x3, so we can deduce that the transaction variable T1 take value 1. But if we assign value 1 to x3, we can infer that, we can deduce that T1 take value 0. So this is easy to see that. We just had to see the different verified constants. So if as x2 is equal to 0, if x3 take value 0, so we have T1 can take value 1. But if, as we said here, if x3 take value 1, T1 take value 0. Here, if x3 take value 1, this constraint is falsified, so T1 take value 0. So this is an example of factoring that can be performed by using this verified constant. So we have another situation here is when assigning value 1 to item variable x1. So here, as a final result, we get 3 frequent item sets described by the following. The first item set is E1 with the cover T2, T3. The second item set is E3 with the cover T2, T3, T4. So all the transaction variable with the value equal to 1, and the empty item set with cover all the transaction present in the databases. So we can also add other kind of constraints to express other properties. For example, here we can add what we call the closedness constraint. So to ensure that the item set is closed, frequent and closed. So this constraint ensures that the item set will be closed. So these models have several advantages, but also some kind of drawbacks. For if we consider the different advantages, first we have a very intuitive CP encoding. It is very intuitive. In terms of genericity, many constraints can be expressed and added easily, and we can get some efficiency in case of tight constraints. But this model has some limits in terms of memory and scalability. First, it requires an important, as you can remark here, we need an important number of variable and constraint to encode, for instance, the frequency mining problems. So here we need n plus n variable and n plus m constraint only to encode the frequency mining problem. So without considering the redundancy constraint. By considering only the coverage, the frequency, so we need n variable item variables and m transaction variable. So we have n plus m variable in total, and n plus m's constraint to encode all the problem of mining frequent patterns. So we have a huge number of constraints, of reference constraints, but this huge number may cause some scalability issue. So we have to find some trade-off between genericity and efficiency. So the question here is to conceive or to have a CP approach, CP solver to tackle very large data. So the major issue here, the main challenge here, is to have a scalable CP solver. So to address this issue, so we have proposed in recent work the first global constraints that encode efficiently the problem of closed frequent item set mining problem. So the nice property of this global constraints is that this constraint requires neither reified constraint or extra variable to model these problems. More recently, Pierre Schotz introduced a new global constraint called cover size for computing the exact size of the cover of an item set. So in closed pattern, we have no access directly to the cover of the item set. So this limits the use of this global constraint because you cannot impose a constraint on the cover. So the proposition of Schotz and its team is to model explicitly the cover item set. So this new global constraint offers more flexibility in modeling problem, as we can impose some kind of constraint on the covers of this item set. So I will not detail this proposition, but I will focus on our proposition, which called closed patterns. So here, in terms of modeling, we use a vector of Boolean variable for representing item set, as in the CP4EM models. But the main difference here is we have just this kind of variable without any extra variable for representing, for instance, transactions. So closed patterns holds if and only if we have the following condition. So if the frequency of the pattern is greater than or equal to some thresholds, and the pattern X must be closed. So solution to the closed pattern are all the patterns that are frequent and closed together. So let me introduce you the notion of closure extensions. So the closure extensions is used for mining closed items as follows. So if some pattern P is a closure extension of some pattern Q, and none of the proper superset of P is a closure extension of Q, then pattern P union Q forms what we call a closed pattern. So this property is mainly used by closed pattern as a filtering algorithm. So in terms of filtering, we have the following three rules. So we denote by X plus the set of all items that are present. That means that all the variable items that take value 1. Those that take value 0 will be designed as absent items. And the remaining variables are called free items. So these variables are not instantiated to. So we have the following three filtering rules. The first rules here remove value 0 from the domain of a variable associated to item I if item I is a closure extension of X plus. I will detail all these rules on example. The second rules filters value 1 from the domain associated to item I, if and only if any extension of item set X plus union I become infrequent. So if we have a frequent item set X, and if we extend this item set with item I, and this new item set becomes infrequent, so we remove value 0 from the domain of I associated to the variable I. Third filtering rules removes the value 1 from the domain of the variable xi if and only if the cover of any extension of X plus union with I is a subset of the extension of the item set X plus with item G, but G is an absent item. So if we have a cover of any pattern extended with a free item I is included to the cover in the cover of an item set if it is extended with an absent item, so we can infer directly that this item cannot be frequent. So we can remove value 1 from the domain of xi. So in terms of complexity, we have a cubic complexity, which is given here. So I will not detail this complexity, but you can find more details in the paper that appears in CP 26. 6C 216. So let me show you how it works by considering the following data sets with 6 items and 6 transactions. So if we suppose that, so we have, as we said before, we have the two representation, the Boolean representation and the classical representation of the data set. So if we suppose that, so here we have, so in terms of modelization, so we introduce one variable per items. So here x1 will be associated to the items A, x2 to item C, x3 to item D, and so on. So now, if we suppose that x1 is equal to 0, that is, item A is not present in the item set, and suppose that x5 is equal to 2, so that means that we have our current item set is equal to W, okay? Because the variable associated to item W is equal to 1. So now, sorry. So if we set the minimal frequency threshold to 3, thanks to the first rules, okay, value 0 from the domain of the variable associated to item C will be filtered, okay? Why? Because C is a closer extension of a W. So we can see here, it is easy to see that the cover of W union C is equal to the cover of a W. So C is a closer extension of a W. So we can remove value 0 from the domain of the variable associated to item C. So now, rule 2, by applying rule 2, we can remove value 1 from the domain of the variable associated to item Z. Why? Because the frequency of any extension of the item set W with the item Z, okay, will be infrequent, as the frequency of WZ is equal to 2, which is below 3. So we can remove value 1, sorry, from the domain of the variable associated to Z. So we can continue here. So by applying rule 3, okay, we can remove value 1 from the domain of the variable associated to item T. So the reason is that as the cover of TW is a subset of the cover of AW, and A is an absent atom, so we can infer that we can remove simply the value 1 from the domain of the variable associated to the item T. So this is the filtering performed with closed pattern global constraints. So here we give some experimental results on UCI datasets with the following characteristics. So we have, for each dataset, we give the number of transactions, the number of items, and the density of each dataset. So we have made some comparisons with CP model based on reified constraints, so CP for IAM. And we also compare the closed pattern with the most efficient specialized algorithms for mining closed frequent item set, which is called LCM. So all the implementation, we have variant type of implementation. So the implementation based on OR tools can be downloaded from this link website. So on all this experiment, the timer has been set to 1 hour, 360,000 seconds. So if we compare closed patterns, so here we report for each data set, we varied the frequency thresholds. For each data set, we varied the frequency threshold data. And for each instance, we report the number of approximately the number of closed pattern mined. We compare the two approaches in terms of the number of nodes and the runtime, CPU time. So what we can see here is that the main observation is that closed pattern clearly outperforms the refined model, CP4IL. Either in terms of number of nodes, okay, and in terms of runtime. So here we can observe a speed up factor between 2 and 50, which is really interesting. If we consider the number of nodes, this criteria is also in favor of a closed pattern, because as we can reduce, in some cases, the number of nodes explored. For example, if we consider the chess dataset, we can see that here a closed pattern can reduce the number of nodes explored by our global constraints. So the second observation we can make here is, which is the main drawbacks of using the refined model for frequent pattern mining extraction, is the memory assumptions. So here we denote several out of memory when using CP4EM. So this is principally due to the huge number of reified constants. So as you can see, closed pattern here have this nice property because it can tackle a very large data set like those one related to retail or T14 or Connect, for instances. So here, CP4EMs get every times out of memory, while our global constraint closed pattern is able to extract all the closed frequent patterns. So now, if we compare closed pattern with LCM, the more specialized algorithms, it is one of the most efficient specialized algorithms for mining closed patterns, closed frequent patterns. So we can see that here, LCM is very, very, very efficient in terms of CPU times. So it is the best one here. However, we can see that here, that closed pattern is more or less quite competitive as a declarative approach compared to CP4EM models. So here I will consider another problem that appears in data mining approaches. So recently several approaches focused on user-centered and interactive and anytime pattern mining. So the main idea here is to be able to put the user in the mining process and to be able to mine the pattern in quickly. That means in anytime context. So a vital ingredient of this framework is to be able, as I said before, to quickly present a set of diverse patterns to the users. So, as I said before, the output of frequent pattern mining algorithm is too large and too redundant to be useful. So, we need here to produce, a small set of patterns with limited redundancy. So this is the challenge here. We would like to address is to find a set of patterns that is small and non-redundant. So is in other terms, we would like to find more diverse patterns. In the literatures, we can find several works for mining non-redundant patterns. So this work can fall into categories. The first one use post-processing approach to find diverse patterns. So they work on two steps. In the first step, they mine all the pattern and they post-process the output to focus on some diverse pattern by using some measures, similarity measures, to filter all the patterns that are more redundant. Another kind of works use some heuristics to find more diverse pattern. So the main focus here is how to exploit the declarativity and flexibility of CP to explicitly taking the diversity of pattern in the mining process. So this is the main issue here. So in literature, we can find several measures to quantify this redundancy. Here we give some example. So if we have here we have a set of transactions and we have these items. Here we have some item set, two item set A and B. So we can quantify the redundancy between the pattern A and pattern B by considering some relation similarity measure. For example, we can get the overlap between the two patterns in terms of cover, in terms of transaction. We can apply what we call the Jacquard. Jacquard is the ratio between the cover and the union of the pattern in terms of transaction of covers. So here we use the Jacquard index as classical similarity measures on sets. Okay, we use it, as we said, to quantify the overlap of the cover of item set. So we can, by exploiting this Jacquard index, we can formulate new diversity constraint based on these similarity measures to compare between patterns. So here, if we have two patterns P and Q, given some similarity measures based on Jacquard constraints, on Jacquard index, Suppose that we have some diversity threshold value, Gmax. We say that pattern P and Q are pairwise diverse if and only if the jacquard between P and Q is below or equal to the diversity of thresholds. So the main idea here is to push the jacquard constraints during the mining discovery to prune a non-diverse item set. So to achieve this, we maintain a set, what we call here a history of all extracted diverse item set during search, and we have just to constrain the next mined item set to respect the jacquard constraints with all the items that have already been included in H. So the new mining task can be formulated as follows. Given a history H of k-pairwise diverse frequent patterns, so the task here is to mine new patterns P such that the jacquard of the pattern with each element of the history, the jacquard constraints, must be satisfied. That means that the jacquard with P and each element of H, the history, must be below or equal to the diversity threshold value. So, but this is not a good news. This is related to the anti-monotonicity of these constraints. So as I said in previous slide, the several mining algorithms exploit some properties, some kind of properties on the constraint to perform pruning. So the one property is what we call the downward closure or the anti-monotonicity property. But here, if we look at on the jacquard constraints, we can see that the anti-monotonicity property does not hold for this constraint. So if you example, let me show you an example to so if we consider here here we have the lattice of all the item set that can be extracted in the data set. Here, so in terms of legend, we have here first the item set, and after we have the cover associated to the item set, and finally we have the jacquard index associated to the item set. So in red we have the non-frequent item set. For example, we can see that this pattern are not frequent according to the frequency threshold theta, which is equal to 7 here. And the green box here are related to diverse frequent closed item set. And the dash box represent all the non-diverse frequent closed item set, all those having jacquard index below some threshold value, which is fixed here to 0.198. Sorry, 9. So if we initialize the history to the item set BA, and we set the Gmax, what we call here the diversity threshold value, to this value, we can see that the jacquard of the item set AA with respect to the history H, which is located here, okay, its jacquard is equal to 0.27, which is greater than Gmax. But its superset item set ACE has a Jacquard index which is below to Gmax. So if we prune here this pattern, so we can lose this one as this its super item set maybe diverse with respect to the Jacquard index similarity measures. So from this example, we can clearly see that the anti-monotonicity property of the Jacquard constraint does not hold. So how to do in this case to have an efficient pruning? So the main proposition here is to use two anti-monotonic relaxation of the Jacquard constraints. So we have two relaxation. First relaxation is based on lower bound, which allows to prune all non-diverse item set during search. We have another relaxation which is based on an upper bound of the Jacquard index. This upper bound enables us to find patterns that necessarily satisfies the diversity constant. So let me show you how it works. So I will pass to the next slide. As I said before, the Jacquard constraint, the Jacquard index, the Jacquard constraint, the anti-monotonicity does not hold for the Jacquard constraint. So we introduce two relaxations, a lower bound relaxation and an upper bound relaxations, to be able to have some nice property for pruning. So the great appeal of this approach is that we can able, as I said, to infer some monotone and anti-monotone properties, which can be efficiently pushed in CP framework, even if the Jacquard constraint itself does not satisfy this property. So we have the monotonicity property on the lower bound. So let H be an element from the history. So for any two patterns, P and Q, such that P is a subset of Q, so the following relation holds. That means that a lower bound is monotony increasing. So this property is very interesting. So what we can infer here that if the lower bound of P with H is greater than the diversity threshold value, so we can deduce that the Jacquard is also greater to the Gmax value. So P cannot be diverse. So this property will be used to perform prunings. We have another nice property on the upper bound, which is the relaxation, upper bound relaxation of the Jacquard index. Here we have some what we call an anti-monotonicity. So as before, let H be an element and an item set from the history. For any two pattern P and Q, such that P is a subset of Q, we have the following relationships. So this means that the upper bound decreases only. Okay, so if the upper bound of a pattern with respect to some element H is lower than the diversity threshold value, we can infer that Jacquard of this pattern is also lower than Gmax, as the upper bound is an upper bound of the Jacquard. So we can infer that P is diverse. So by using this property, we can So by using these two property, we can perform pruning, particularly by using the lower bound in the mining task. So we have a new mining task. You can formulate a new mining task, which can be given expressed as follow. So given a history H of a pairwise diverse frequent closed pattern, so the new task here is to mine a new patterns. So instead of using the exact Jacquard, we only use a relaxation of the exact Jacquard by exploiting the lower bound. So the new task here is to mine candidate patterns such that for all elements of your history, we have the lower bound must be below the diversity threshold value. So when, moreover, when the upper bound is lower to the Gmax for all the elements of the history, we have some certification about the diversity of the pattern P with respect to all the elements of the history. So in this case, we can infer that the Jacquard constraint is fully satisfied. So how this framework can be exploited in CP models. So we have here, I will not go to the details, but I will give you some overview on how it works. So here, I forgot here to precise that initially the history H is empty, and we will will update this history H with a diverse pattern by considering this following condition. So from this new mining task, we have proposed this year a new global constant noted closed diversity. This global constant can be seen as an extension of the closed patterns by adding some condition to ensure the diversity between patterns, pairwise, by considering pairwise patterns. So as in closed patterns, we use a vector of Boolean variables for representing item sets. We have the following conditions for closed diversity. So closed diversity given a set of pattern, a history H, and some three-shot values related to the Jacquard. So this constraint holds if and only if, as for closed patterns, the item set X must be frequent and closed, but also we ensure that the item set X must be diverse. That means for all the elements of H, we need to have that the lower bound of X with each element of H must be below or equal to the diversity support thresholds. So the propagator of this global constant, this new global constant closed diversity, exploits the filtering rules of closed patterns. It also uses our lower bound to remove items that cannot belong to a solution in terms of diversity. So let me explain you more rapidly these two filtering rules. The first rule is rather simple. We remove value 1 from the domain of the variable associated to item E if and only if there exists an element from the history such that the lower bound, when extending this item set with I, we get a lower bound greater than Gmax. So in this case, we have the certitude that E cannot be, that this new item set cannot be diverse with respect to our lower bound and to the Jacquard measures. The second filtering rules, here we remove value 1 is related to the absent items as in cross pattern, but we exploit the lower bound to infer some kind of things like removing here value 1 from the domain of the item set I. So if we have an item I that appears in xdev, here xdev is all the set of items that have been filtered by the first rule, filtered by the lower bound, such that the cover of any extension of the item set with I is a subset of any extension of the item set X with K, such that K is an abstract items and appear in xdev here. So we can prove this property easily, that the lower bound of X, of the extension of X, of the item set X with I is greater than the lower bound of the item set X extended with item K, such that K is absent. So, and this one, as the lower bound of the extension of the item set K, item set X with K is greater than Gmax, so we can deduce that the lower bound of the three items, for the extension of the three items I with X plus will be also have a lower bound greater than Gmax. So we can remove value 1 from the domain of the variable XA. So with this, so we have the two following filtering rules in addition to the three filtering rules performed by closed patterns. So now, how we can here we showed you how the lower bound can be exploited to filter the domain of the variable, but how we can exploit the upper bound. So as I said before, the upper bound exploited only to prove the satisfaction of the Jacquard constraint, since if we have for example, if we would like to extend the item set X with item E, and the upper bound of this item set with respect to the history H is lower than Gmax, so we can see that here. We can infer that item set, the new item set X extended with item I satisfies the Jacquard constraint. So with this idea, we proposed a new heuristics, which is a new heuristics. This heuristics selects the next frequent items such that the following property is satisfied. So the main idea here is simply to favor the satisfaction of the Jacquard constraint when extending any partial assignment of an item set. So if we can find one items that extend the current item set to new one with satisfying this the upper bound condition, so we have the guarantee that this item set will be diverse with respect to the history H, but all the superset of this item set also will satisfy the upper bound. So in this case, when you find what we call witness item, so this item, an item which satisfy this condition, so all superset of this item set will also satisfy the Jacquard constant. So what we do here is to generate only the first closed diverse item set pattern in the subtree, and add it to the history H, and to continue the exploration for the remaining search space. We have also proposed a new baseline branching heuristics, which select the next 3 items having the minimum support, estimated support. So I will not detail this, but let me show you some experimental result to get with this framework. So we have made the experiment on the same data set, UCL data set. We compare the result of closed diversity with closed patterns. The main idea here is to show how well the new global constraint reduce the output, and what is the incidence of adding this diversity property in terms of runtimes. So all the implementation has been done in Choco server, and we have set the timer to 24 hours, so 1 day of computing. So as we can see here in this, so here we report the number of patterns extracted by closed pattern. Closed pattern here is the result of closed pattern in this column 1. The result of closed diversity is given here by this column 2. We set the minimum threshold value to this value, and we used the heuristics Minkow's, which select the item according to their frequency. So as we can see here, so the closed diversity pattern enables to reduce more drastically the number of patterns. So this result highlights the great discrepancy between the two models, with a distinctly lower number of patterns generated by closed pattern in thousands in comparison to closed pattern, where the number extracted pattern is in millions. For example, if we consider here Chase data set, we have 22 million of closed pattern, while with closed diversity, we get only 65 patterns, which is very important, interesting. So this reduction is more or less amplified, greatly amplified, especially when considering for small value of theta on this dense data set like chess, mushroom, and so on. So if we look at the very sparse data set like pumps, T14 and retail, so closed diversity still output fewer solutions, as we can see here, but the difference is less pronounced. This can be explained by the fact that on this data set, where we have few solutions, basically, almost of patterns are more diverse. So the reduction in terms of pattern is not very huge, contrary to the dense data set, where here the explanation for the large reduction can be explained by the density of the data set. This probably explain the good performance of the closed diff in terms of the number of pattern reductions. So here the main message here is that as the number of closed pattern increases with a dense data set, redundancy among these patterns increase as well. So a closed pattern enables to filter more drastically than closed patterns. So if we consider, and I will finish by this slide. See here, sorry. So if we consider the runtime, so we have closed diversity exhibits different behaviors. So if we consider dense data set, we can see that closed diversity is very efficient than closed pattern. And we have up to 3 orders of magnitude faster when comparing with closed pattern. So here, for example, if we consider a chess data set with theta equal to 10%, so closed diversity complete the extractions more or less than about 700 seconds, but closed pattern get out of memory. So these are very nice results in terms of runtime. But if we consider sparse data sets, so we have some inversion. That means that closed diversity can take significantly more times as compared to closed pattern to mine all diverse frequent closed items. So this behavior can be explained by the fact that on this instance, almost as we said before, almost all frequent closed patterns are diverse. So with respect to our lower bound relaxation. So no solution are rarely filtered. So while the lower bound, the computation of a lower bound gradually penalized the simple solving process. So the main result here is that closed diversity enabled to generate less pattern in comparison to closed pattern. On dense data set, closed diversity is up an order of magnitude faster than closed pattern, but on sparse data set, closed diversity can take significantly more times to extract all diverse frequent patterns. So I will skip all this. So I will get to the conclusion. Sorry. Oops. So as a conclusion, so here in this talk, we focus on the CP paradigm, constraint programming approach, but other well-known modeling paradigm exist in AI, such that SAT, integral linear programming, or SP models. So we have a growing interest for exploiting them in data mining, machine learning. We have a wide range of tasks that can be modeled or expressed using such kinds of formalism. So the main, as we said, the main advantage here is the reuse of solver technology, and in sometimes we can outperform state-of-the-art approaches. So nevertheless, scalability is the main issue of this paradigm. So for me, I will have two main directions. So to provide novel encoding of propagator, like closed pattern, closed diversity, cover size, or to get some form of hybridization with a different paradigm. For instance, we can, for instance, combine the CP with the ALP approach to perform wells and to tackle a large data set. Thank you. If you have questions, we have very few times to.
Yes, Samir, there is one question that appeared during your talk when you were presenting constraint programming. You have it in the Q&A window.
Okay. Sorry. I will stop. Okay, question. Please, what is the solution if all constraints of the problem are contradictory? So what you mean here? You mean that if there is some violation of the constraints? So in this case, we get no solutions. So as our framework does not allow the violation of the constraints. So I don't know if this is if the answer is satisfactory.
Yes, it is. Do you have any question? Any other question? Or in this case, maybe you can ask question after the break. Samir will be here also.
Yes.
Because I think everybody needs a break maybe. Thank you very much, Samir, for this lecture. So let's meet in half an hour for Najib Lazar's talk about constraint acquisition. Thank you very much. Maybe you have another question. Maybe one question appeared in the meantime.
Okay.
You can maybe answer.
The history updates are all the previous history taken in consideration? Yes, yes. What I said here is that when we in the mining process, each time we find a diverse close pattern or diverse pattern, we put it in the history. So this new solution will be taken into account to discover, to mine other diverse patterns. So the edge is growing during search. But we can impose some size. Huh? We can constrain the size of the edge, but here we have not performed this kind of experiment.
So thank you, Samir. Let's close the first part of the session and let us meet again in this Zoom session in half an hour after the break. And if you want to talk with the speakers, you can meet them in the Discord platform right now. There are a few speakers connected, so don't hesitate to go and meet them. Thank you. See you.
Thank you.